Okay, let's learn about the substitution method. Here's just kind of a fun image of Indiana Jones trying to take the golden idol from the ancient Indian ruins, and he needs to replace the idol on this weight-sensitive stand that it's on, the stone stand. So he's got a bag of sand or some other kind of weight that he's going to put in place of this idol, and if the weight is the same, then the trap won't go off. And he needs to make sure that his substitution is equal. So if the weights are equal, he's going to be safe. What we will be doing with the substitution method is kind of like that. We need to substitute things that are equal and eventually find their values. Let's look at some problems. Okay, here are 6 problems, and I've chosen to look at 6 all at once to just kind of guide us through the first step and be able to take a look at several different problems and what you would choose to do first in the first step. Our very first step is going to be isolate one of the variables, and it doesn't matter which one or in which equation. So let's take a look at problem number 1, for example. The easiest variable to isolate would be variable x in the first equation, because its coefficient is 1. I'm not going to have to do a division step to get it isolated. All I would have to do in that equation is subtract the 3x from both sides, which would eventually give me x equals negative 10 minus 3x. So I'd have this equation here. X equals negative 10 minus 3y. This expression is what x is equal to, and since the system x needs to be the same for both equations, then I could replace this expression that I just put parentheses around and replace x in the other equation with it. That's where we'll go from here, but I want to look more at what step 1 is all about. So what you do is you try to identify the easiest of the four variables to isolate. In problem 1, that was x in the first equation. What is it in problem 2? Well, none of them really look that enticing, but since the coefficient of y in the second equation is negative 1, that's probably going to be the easiest. If I try to isolate, say, y in the first equation, then at some point I'm going to have to divide every term by 5, and that's going to give me some fractions like 6/5 and 8/5, and I don't want to have to deal with those, so I would rather just isolate the y in the second equation. What would you isolate in the third equation? I hope you thought to yourself, x in equation 2. Sorry, I meant the third problem. Let's take a look at the fourth problem. What would you isolate first there? I hope you thought to yourself, y in the first equation. This should start to come naturally to you. What is the easiest thing to isolate first? Take a look at 5. What would you isolate first? I hope you thought x in the first equation. All of these have a coefficient of 1, making them the easiest to choose. What would you choose in equation 6? Problem 6. I hope you thought to yourself the y would probably be the easier one. Okay, there are some other things that might be easy to do if we know how to use the elimination method. And later when we do look at the elimination method, I'll talk about how it is an improvement over the substitution method. But we need to understand substitution skills because half of the elimination method relies on knowing how to do the substitution method. So step 1, isolate one of the variables. We need to be able to make sure that we know which is going to be the easiest to work with. Okay, here's my first problem that I'm going to actually work all the way through. So following step 1 that we saw on the previous screen, which do you think is going to be the easier variable to isolate at the beginning? Well, in this case, I've actually got 2 choices. I can either isolate y in the first equation here, or I can isolate x in the second equation. Both are going to make this rather simple. I'll just go ahead and solve for y in the first equation by subtracting 2x from both sides. And I'm going to subtract 2x from my missing x term here. I'm not subtracting it from the 1. 1 is a constant, and I can't subtract 2x from a constant. This is going to eliminate to 0x, and so I've got y is equal to 1 minus 2x. If I was doing the graph and check method, I've actually solved and put this in slope-intercept form. I'm not going to graph this though. I want to now use this expression that y is equal to and replace y in the other equation with that expression. So now I will have x plus 2 times the quantity 1 minus 2x, and all of that is equal to 5. Okay, all I have done is replaced y in the second equation with the expression that I know it's equal to, and that's a fair substitution. Kind of like Indiana Jones's replacing the golden idol with a weight that it's equal to. This helps and actually gets me closer to finding values because now I've got an equation with only one variable in it. That's something I can solve. Let's use the distributive property to simplify this, then combine like terms and see if we can eventually solve for x here. So x plus, I need to use distributive property and get 2 minus 2x is equal to 5. Now I need to combine like terms. I've got x terms on the left side, so that's going to make negative 1x, or just negative x, plus 2 equals 5. And let's see, I need to subtract 2 from both sides. So now there's a 3 over here and a negative x there. So if I multiply both sides by negative 1 or divide both sides by negative 1, I get x equals negative 3. I now know the value of x for the solution. That actually gives me half of the answer. I'll come up here and put half of my answer. I should now go back and figure out what is the y coordinate for the solution. Well, I've already got an equation right here that's solved for y, except it has another variable in it. But I now know the value of that variable, so I'll replace x with what I know its value is for the solution, which I just figured out was negative 3. So I will now simplify the right side and should have the value of y for the solution. Negative 2 times negative 3 is actually positive 6, and so the solution should be y equals 7. So then I can bring that up here and put it in my solution, and I know that those two lines should cross each other at negative 3, 7. Here is another problem. I'll try and go a little more quickly through this one, but pause and make sure that you understand each step of the way. First of all, which variable should I isolate first? That should not be obvious. I need to solve for x in the second equation. I could solve for other ones, but I'd end up with fractions and don't want to have to deal with that. So I'll add 4y to both sides, and now I've got x is equal to 9 plus 4y. This expression is going to be replaced, it replaces x in the other equation. So x is going to become 9 plus 4y over in the first equation. 2 times 9 plus 4y, that needs to be distributed in a moment, plus 5y equals 5. So now I have an equation that only has y's in it. Let's distribute and simplify and solve for y. So distributing, I get 18 plus 8y plus 5y equals 5. Combining like terms, I'm going to get 13y there. Oops, 13y is equal to 5. Subtract constants from both sides. So 13y equals what? Negative 13. So y must be negative 1 after I divide by 13s. That simplifies to 1y, and over here it simplifies to negative 1. I now have part of the solution. I know the negative 1 goes in the y coordinate. Now I should figure out the x coordinate, so I will take my value for y and substitute it there, and that would give me x equals 9 plus 4 times negative 1. So I get x equals 9 minus 4, so x must be 5. Now I've got my full solution, putting that into my ordered pair that's the solution for the system. Here are the two problems I'd like you to do for the warm-ups. Good luck, students.